thank you very much for the introduction and for this invitation. I will be, somebody asked to the previous speaker, there are different ways of addressing robotics. One is a very utilitarian way of doing robotics, so you build robots to solve real-world problems. Another way is to use robots as a sort of models to investigate biological questions, including cognitive questions such as consciousness. Now, I cannot really tell much about consciousness, but what I decided to do in this talk is to take the second approach, so to show to you how we can use robots to address some biological questions. And instead of focusing on one or two or three specific examples of robots that may have evolved some sort of relatively complex cognitive functions, I decided to show to you many cases of robots that we have been evolving in the lab. And some of these cases are more sophisticated than others. And it's a little bit up to you to see what we can do with this approach, how far we can go, and whether some of these robots may start to manifest some of the ingredients that we need or that we think are necessary for the evolution of consciousness. My stand on this problem is that nothing makes sense except in the light of evolution, as it has already been said in the past. So my laboratory is very active in many aspects of robotics, including utilitarian aspects of robotics. So this is an artistic view of what we want to do. We focus quite a lot on biomimetic approaches, and we develop a lot of flying robots, although you will see very few flying robots in my presentation on evolutionary robotics today, because for technical reasons it's difficult to evolve them. And I'm interested also in the evolutionary approach, the design of robots and control systems. Okay, so Eamon Harvey made an excellent job this morning in explaining the basic evolutionary cycle that we use in evolutionary robotics, and I want to repeat that. I want to show to you, however, an example of how you can apply that evolutionary loop to a very simple robot. Imagine that you have a robot, a circular robot, and you want to evolve the capability of doing collision-free navigation. You start with a generation of random genomes corresponding to different control systems, and one of the main ingredients is that all the robots in the initial population have diverse genotypes and diverse behaviors. So you see here two robots of the first generation. The first one was rotating on the spot. The second one rotates on the spot, goes towards an obstacle. This one, since the goal, the reproduction criteria is to avoid obstacles, will have less offspring. And this guy will not make any offspring because it doesn't move. Actually, it follows my hand, so it does the opposite of the reproduction criteria. Now, if you let evolution select the best individuals out of the men in the population, after a few generations, which in this case is 24 hours of evolution on the robot, you find individuals like this that have a neuronal system that has not been designed, it has been evolved, capable of smoothly moving around the environment. So in all the experiments that we'll be showing from now on, including in this one, the genotype of the robot encodes the topology and the strength and the parameters of artificial neuronal networks, which are caricatures of the real nervous system, as Inman put it very nicely before. Nonetheless, it is a distributed system. It's capable of in some cases, of synaptic plasticity. It has a lot of dynamics and memories that can encode states of the system, encode variables of the system as it moves around, which may eventually be interpreted, depending on your stand on this, as a representation planning consciousness. Now, let's take one of the beautiful things about evolution is that the role of the human designer can be reduced to a very minimum. And the environment and the robot morphology and sensors can play a very important role in the results that you get out of this evolutionary process. So let's now take the same robot and put it in a different environment, which unfortunately you cannot see here because of the lighting. We have an environment where the same robot you've seen before can, if the robot goes to that black spot on the top corner there, it can recharge its own battery. So the robot has virtual batteries that have a duration of approximately 20 seconds. If the robot does not go on the black spot, after 20 seconds, it dies, and it can no longer accumulate fitness by moving the wheels and avoiding the walls. However, if the robot happens to go on the black spot, it will continue to accumulate energy or fitness point for reproduction, if you like, by recharging the battery and moving in the environment and avoiding all the walls. So we use the same reproduction criteria or fitness function as we did earlier on. We monitor the position of the evolving robots with a sort of GPS, internal GPS. And what you find is that after 240 generations, it's a bit longer than the previous evolutionary case, we find a robot that if you put anywhere in the environment, it will move around the environment. It will not go to recharge its batteries, but it will go to recharge its batteries just approximately 2 seconds before the batteries are expired. You see, it goes to the recharging station. It does not stay on the recharging station. It goes out of the recharging station, and it keeps moving around while avoiding the walls. So this robot somehow has developed the capability of locating where the battery charger is, and it's not a trivial task because from the sensor's perspective of the robot, there is not a very nice gradient of light. The robot has somehow, many areas in the environment look the same, so the robot has somehow to encode where it has been before and keep a trace of the trajectory it has kept. And the question is, how does the robot do it? Since we are monitoring the position of the robot as it moves around, the evolved robot, we can also monitor the activity of some of the internal neurons. These are neurons that are not connected directly to the motors and to the environment, but they just have internal dynamics. And to make a long story short, what you see here is the activity map of one of these particular neurons. When you see the grade levels indicate the activity level of that neuron depending on where the robot is in the environment. So the square is the environment. And for example, if the robot is here, that neuron will have a very high activity rate. You see white means high activity rate. Instead, when the robot is on the top corner on the left, which corresponds to the charging station, that neuron will have a very low activity level. And what you see is that if we repeat the measures of the activity of this neuron as the robot freely moves in the environment, we see that, first of all, this neuron does not change its activity level depending on the charge of the battery. So this neuron does not respond at all to the battery level, which is strange because the battery level is the most important indicator for the survival of the organism. However, this neuron changes its activity pattern depending on whether the robot is facing the charging station here or facing the opposite corner. So depending on whether it's facing the battery station, depending on whether it's facing the opposite corner, this neuron will have different states. And what this neuron does is that it encodes the location of the robot in the environment. As a matter of fact, the robot will always approach the charging station through this gate. It will never approach the charging station from these areas where you see the white walls, if you like. It's a sort of neuron that encodes the location, like a sort of place cells that encodes the location of where the robot is. And as soon as the robot faces with its sensors the opposite side of the charging station, this neuron will change the activity level, and it basically encodes the distance of the robot from the charging station. As the robot moves far away from the charging station, it is telling the robot, look, you're moving farther away, farther away. As soon as the robot moves back and faces the charging station, this neuron will tell the robot how to drive safely towards the charging station. So this is not a place cell neuron, as people have found in the rat hippocampus, but it is a neuron that encodes the locations of the robot in the environment, and therefore, computationally speaking, it does the same thing as the place cells do. And this happens simply by putting a robot within a neuronal network and evolving this robot in a situation where the robot has to locate a strategic location in the environment and periodically go back to that strategic location in order to ensure its own survival. Now, this robot has no vision. It only has light sensors that are not capable of, if you like, establish correlations among themselves. Now, we know that a lot of interesting, at least for us, forms of life in this planet use light, as it has been already said yesterday. And if you use light and if you are capable of looking far away and distant in the environment, you may start to be able to catch or to discover correlations that may enable more complex behaviors. Now, what we are going to do here now is to evolve robots that have a camera. This is a very primitive sort of camera. It's a linear camera. It's a one single camera, despite the two holes. In one of these two holes, there is a chip that simply detects the overall intensity of the light in the environment, and it adapts the sensitivity of another camera, which is sitting in the other hole, and that camera has one array of 64 pixels spanning 36 degrees visual field. It's a black and white camera, so what you see here, this robot now is looking at the black stripe here on a white wall. So all the pixels are very active on the different sides, and here you see the black stripe. Now we know that all the animals on this planet are not interested in absolute light intensities. What they are interested in is discontinuities or contrast. So the very first thing that we do is that we apply a Laplace filter. It's a mathematical operation that allows this robot to detect only the areas of contrast, and the areas of contrast are here. We then simply take the absolute values of this area of contrast, and we send these values as activities, as pulses, to the internal neuronal system that eventually will affect the speed of the wheels of this robot. Here we are going to evolve a different type of neuronal network, which is much closer to biology. It's called the spiky neuronal network. It has complex dynamics. And we know that spiky neuronal networks are interesting because they are biologically plausible, but they are also very difficult to design by hand. So what we decided to do is to investigate the question that we were asking was whether spiking neuronal network would use spike in time as a way of communicating with each other, or they would use firing rate, which is a big debate in the neuroscience community. I won't go into the detail of this. I simply want to show to you that if you evolve, if you encode in the genotype the topology of this neuronal network and some of the parameters of these spiky neurons, you put the robot in this arena, you use exactly the same fitness function as for the previous robot that I've shown earlier. Then, after only a few generations, approximately 40, you will get a robot that uses vision to locate the distance from the walls and safely navigate around this environment. Now, in order to, you can solve this problem in a very simple way. If the stripes have all the same size, the robot will use the distance between the stripes as a proxy to the distance to the wall. So in order to evolve a non-trivial behavior, you have to have irregular spacing of the stripes, so the robot cannot count on that sort of invariance. Now, we had this robot, and then we looked, just to give you a feeling of what happens inside the brain of these robots, we wanted to understand whether these neurons were using a firing rate or firing time as a way of communicating with each other. So we had 10 internal neurons, you see them on the top columns, and we counted the spikes per second as the robot was moving around. And we saw that they have very different variety of spiking rates, from very high, almost bursting rate, to almost to basically zero activity. Some of the neurons were not active at all while the robot was moving around the environment. So then we looked at the interspike variability, so whether the spiking is periodic or whether it is spread across multiple time intervals. And we saw that some of these neurons had a very diversified spiking rate, whereas other neurons were spiking at very periodic intervals. So we thought, okay, if we lesion the neurons that spike with a very high variability, probably the robot will not be able to perform the task anymore as it is doing now. And it was not true. So the high variability or diversity in the spiking rate was not what was really counting in this robot. And then we found that we could kill or lesion 30% of the activities, 30% of the neurons in this brain, and leave the robot with intact behavioral capabilities if we killed only the neurons that were spiking in a way that was not correlated with the spiking activities of the postsynaptic neurons. In other words, there are a few neurons out here. Some of them, there are 3 neurons actually. It's 1, 5, and 7, that whenever they spike, their spiking activity is never correlated with the spiking activity of the neurons they connect to. If you lesion those neurons, independent of their activity, then you get a robot that, despite having 30% of the neuronal mass less than the original evolved robot, is still capable of moving around. And now you see that the only difference is that the behavior of this robot is a little bit more, less smooth. But of course, if you take 30% of your dynamics of the brain out, you depend much more on the sensory experience that you get, and therefore this robot is much more reactive to whatever it perceives. but still it can move around. So it seems that the correlation of spiking activities in evolved spiking neurons plays a very important role, at least in this case. We then said, okay, well, can we evolve using the same fitness function, the same spiking neuronal network, can we evolve a control system for a robot that has more complex dynamics than a robot standing on the wheels? And for doing that, for testing this, whether we could do that, we took a blimp, a small Zeppelin, if you like, and we equipped the Zeppelin with the cameras in the front, exactly the same type of camera. We just changed the lenses so that the field of view was much larger. Instead of 36 degrees, it's 150 degrees, which you may need if you have a large body and if you have very complex dynamics. You want to be able to see quite a lot around yourself. And we repeated the experiment in a room. So the robot had batteries that lasted only 4 hours. And everything was running, the evolution was running in the microcontroller that was sitting on the robot itself. And I only had the student going every 4 hours to change the battery of the robot and let it evolve indoor. Now, how do you measure the fitness of a flying robot? If you have a robot on wheel, you can measure whether the robot is moving out and avoiding obstacle by using the odometers or encoders of the wheels, and you can use sensors, contact sensors, to know whether it has collided or not. With a flying robot, it's more complex. So what we came up with is that we equip the robot with an anemometer in the front. It's this one. The anemometer is a passive propeller. As the robot moves, flies forward, the anemometer will turn in one direction. And the rotational speed of the anemometer is proportional to the speed of the robot, to the translational speed of the robot. If the robot stops, or if the robot moves in one direction or the other, or it bumps into an obstacle, the anemometer won't spin anymore. So the fitness of this robot, or the criteria for selection, is simply the amount of rotations that the anemometer has made over a fixed amount of time, which is 2 minutes for this case. Every individual lived only for 2 minutes, and it had to maximize the rotational speed of the anemometer in one direction. And only after approximately 50 generations, that was in this case, I think 3 days of evolution, you can see our robot. It can very nicely fly around this arena using only the visual information. The robot has very complex dynamics, so if you can imagine that you can only look in the front, it's amazing how accurate the neuronal network is in, if you like, controlling or taking care of the dynamics of this robot. We can look at this robot flying from the side here. Here you see actually the anemometer is this one on the bottom. You see it's not on the front as in the drawing. The anemometer is the one on the bottom, that passive propeller there. You can see that the robot not only avoids the walls, but avoids anything that you can put in front of it. So I have a student standing there. Maybe I show to you. We can put a hand in front of the camera of the robot, and the robot will try to fly in order to avoid a hand. And you can also do one thing. You can put the robot against the wall, and you will see that the robot will move backward, and then it will resume the flight and fly on. So there has been no design by a human here. It's a simply evolved a control system that has a slightly more complicated neural network that takes into account all the constraints of its morphology. You can also shrink the whole approach and use it for much smaller robots, but I will skip this. It's just the same thing. So we do also artificial evolution on sugar cube-sized robots. Everything runs on board, but I'll skip this, and I will move on to a different example. Active vision. So far, the visual system of the robot was solidal with the body of the robot. But many animals are capable of looking around and deciding what we look at. So we may decide that we look at that direction before actually moving in that direction. So we can do active exploration of our environment. And this is a quite powerful capability, sensory motor capability that we have. So what we decided to do was to investigate the role of active vision using an evolutionary approach again. We took a mobile wheeled robot. Here it's slightly larger than the previous one. We equipped it with a Sony pan tilt camera, so the camera can do a pan and a tilt, and they can also zoom in and out. And we had a simple neuronal system that received input from a set of neurons whose receptive fields were spanning the entire field, or a portion of the field of view of the camera. We had proprioceptive sensors, just like any animal has, about the position of the eyes in the head and about the position of the head in the body. And these proprioceptive sensors were telling the robot the neuronal network, the pan and tilt angle of the camera. And then we had some memory units, so neurons that encode the internal dynamics of the robot. And the output units of this evolved neuronal network were not only controlling the wheels of the robot, but also controlling the pan, the tilt, and the zoom in and zoom out of the camera. So the robot could at the same time move and decide where to look at, which would affect the sensory input that the robot receives. Now, if we put the robot in an environment like this, in an office, and then we use the same fitness function we have used so far for all the robots I've shown so far, you see that the robot has, therefore, it can maximize the fitness by moving around this environment. So the fitness is maximized if it can manage to move forward the speed of the wheels, to move forward the body, by counting the rotation of the two wheels. But you can see that the robot can look at many different things here with the camera in the office. It can look at many different things, like people passing by, like the window, like this. But in fact, the robot can only move within this very small confined space. So the question is, what will the robot look at? And so we started evolution, and as you're going to see, as you're going to see here in the video, some of the individuals in the initial generation, they pay attention to things that are not relevant for the task. So this robot is paying attention to the sun coming through the light, through the window. This is interesting, but it doesn't help the robot to move around, avoiding the walls. So this robot will make very few offspring for the next generation. Then you have a robot here that always looks up, and then here I'm filming the robot with the camera, and the camera is on a black pole, like that one. And as soon as the robot can see this black stick, this black feature, we'll stop at it, look at the camera. But this is not good enough for moving around. And then you see that after a few generations, the best evolved robots, what they do is that they look at the edge between the wall, the white wall on the ground, and the floor. And they always keep track of this edge. And they also sometimes look ahead, because this is the most informative piece of information you have in this environment to know how far you are from the wall and to move ahead. And sometimes they also turn the camera, when they turn to the right, they move the camera to the right to see if there is any obstacle, and then they keep track, they focus back again on the edge. So it's a quite interesting sensory motor coordination here, which is effective. And we also did experiments outdoor in a number of different environments. We can now start to change the body of the robot and go for more complex robots like humanoids. Now here again, humanoids have, in this case, we were working with the Fujitsu robot, and the robot has a pan tilt camera. Now one of the interesting things about leg locomotion is that as you move, the entire environment moves very dynamically. So either you keep your head or you keep your gaze fixed on some object, or everything will move around. And the question is, how can a neuronal system cope with this very dynamic behavior? So evolving a control system for a humanoid robot is not possible in reality, because you would break the mechanics very easily. Evolution operates by repetitive tests of multiple individuals. So if you operate with wheeled robots, it's okay. You can run evolution for multiple days, but not with a humanoid robot. So what we did is that we used a simulator provided by a company for this, and we evolved in the simulation a control system for this robot that can only see through this camera. So the robot is put in this simulated environment. There are a few pillars or columns in the environment, and the task of the robot is to reach that window over there. So there is an opening there. So the robot has to learn how to avoid the pillars, locate the window, and walk towards the window with this very dynamic field of view. The output is controlling the movement of the legs and controlling the pan, the tilt, and the zoom in and zoom out, which is like the focus of attention, if you like. And I'll show to you, maybe I'll show this video. What you see here is the robot perspective, where the robot looks at. This is the movement of the robot from the top, and this is what the robot looks at. And for quite a long time, the robot moves on the spot because it has to locate where the window is. It cannot find it. As soon as it locates it, you see that it starts moving towards the window. Now it lost the window. Now it will get a better perspective, I think. So the window now is larger. And it will start moving towards the window. And then eventually it will reach the window. So you see it gets confidence and it reaches the window very easily there. So this is just to show to you that artificial evolution, when put in the right conditions, in the right environment, with the right type of morphology, it will develop, not right, with a suitable type of morphology, it will develop more complex strategies. You can also have fun with this. And what we did, one of my students evolved, hacked a car game simulator, one of the things that you can do with the PlayStation with these games. And he evolved the driver. So the evolved neuronal network is sitting behind the windscreen at the steering wheel, and it can control the gas and the brakes. What the neural network looks at is just like our eyes. You're sitting in front here. What the neural network is looking at is only this window. So this is the single eye of the neuronal network, of the artificial driver. This is the windscreen. And as before, the evolved neuronal network can control gas, the braking. It can decide where to look at, and it can zoom in and out. In other words, it can focus attention on some detail or simply take a general picture. And what I show to you here is the best evolved driver. You see that before starting, it focuses on the edge of the road, and then it accelerates. And it keeps track, basically it uses its proprioceptive information of the height of the camera to decide how far away it is from the edge. Very dynamic. It's extremely efficient, and it was capable of beating the student who had been playing with this game for several weeks non-stop. Now, all the neuronal networks that I've described so far were not capable of learning during lifetime. So they were only evolved, and during lifetime, all they had was the internal dynamics provided by the recurrent connections in the neuronal network. Now the question is, what happens if you genetically encode this synaptic plasticity, the property of synaptic plasticity that many animals have? Now, in all the experiments that I've described so far, the genetic code, which was just a string of bits, as Iman was describing earlier on, the genetic code was encoding the strength of each individual synapse and the sign of each individual synapse. So we used, for example, 5 bits to encode the strength and the sign of that synapse. Now, you can use exactly the same genetic encoding, but this time, instead of encoding the strength of each synapse, you can encode which one of the 4 types of learning rules that have been found by neuroscientists this synapse will use to change its own strength during lifetime. So as the genotype is decoded into a neural network, the initial synaptic weights are randomly set, just like a newborn baby. It has connections are established and at some random value. Or at least what they have is that what is genetically determined is whether the synapse is inhibitory or excitatory. That's the only thing. And then the strength of the synapse is changing during the lifetime of the individual, of the robot, as it experiences the environment, using one of the 4 learning rules that are genetically decided by 2 bits. And then we have 2 bits that are used for setting the learning rate, so how quickly that synapse will change using that particular synaptic rule. Now, one interesting result of this is that evolution can use different type of learning rules distributed over the neural network, which is very different from what computational neuroscientists do, or people in neural networks. When people in neural networks develop a neural network, they use the same algorithm or the same learning rule for all the synapses in their network. Our brain uses different learning rules depending on where the neurons are sitting in the brain. So evolution here can play with different type of learning rules. So I won't go into the details of these variations of learning rules, but they have all been found in nature. And what we can do is that now we can repeat the same evolutionary experiments that I've shown to you in the first slide, where the robot had to do collision-free avoidance in the looping maze. Now, we evolved the robot this time with this synaptic plasticity, and what you see here, each of the bars is the axis that connect the 2 wheels of the robot, And I plot the position of the robot, the segment, the axis between the wheels, every 100 milliseconds. So what you see here is the trajectory of the robot plotted every 100 milliseconds. The robot, the evolved robot, is put first against the wall in the middle of the looping maze. And as you see, during the first few seconds of its lifetime, it just keeps colliding with this obstacle. And after some time, as you will see in the video, I don't have the video, but after some time, the robot moves backward, and then it starts moving around the looping maze. This is the second loop it does. And you see that the behavior of the robot, which is capable of learning during lifetime using the evolved learning rules, is much smoother than during the first loop. So this is the same robot at the beginning of its lifetime, so to speak, and at the end of its lifetime. Now, since this robot is capable of learning during lifetime, we can now test it in a different environment. So we put the same robot in this environment. To you, it may look similar, but for the robot, it's very different because the lighting condition is different, so there is a much more infrared light in this environment, which affects quite a lot the sensor of the robot. The walls are made of wood instead of polystyrene, as in the evolved robot, so this changes the reflective properties. And third, the geometry of the environment is very different from the looping maze. These are all the three things you can change that can make things go wrong in a hand-designed robot. Now, if we take that evolved robot, we reinitialize the synapses to small random values, and we let the robot learn again without evolving it, you will see that at the beginning it collides with the walls. So it's like a newborn baby, if you like. And after some time, it keeps moving forward. And you will see that the number of collisions decrease over time as the robot follows the walls. Now, this robot here is the same robot that you see here, but its behavioral strategy is very different. Instead of doing wall avoidance, it does wall following, which for roboticists are two different coding strategies or very different behaviors of very different problems. So the same robot put in a different environment learns, so to speak, or develops, so to speak, different behavioral strategies. Okay, now let's look at one of the most difficult problems that I've given robots so far using the evolutionary approach. And this is a sequential task. What we do is that we put the robot in this arena. The robot has a vision system, has the same linear camera we've seen before, and its lifetime is 2 or 5 minutes. I don't remember how much every robot was tested 2 or 5 minutes. And it can gain fitness points only if it is sitting under this light bulb, where the gray area is, when the light bulb is on. Now, the problem is, as the robot starts its lifetime, the light bulb is off. And in order to switch so if the robot goes to this gray area when the light bulb is off, there is no fitness point to be gained. The only way to switch the light bulb on is for the robot to go here towards this light switch. We can detect that the robot is on the light switch if it is sitting on this area. And then when the robot hits the light switch, then the light bulb will go on, and the robot has to go rush here and stay under the light bulb. So we do not program anything. We just evolve a neuronal network. And we evolve the neuronal network in two conditions. One, where the same genetic string encodes only for the synaptic strength, and the robot cannot learn during the lifetime. And two, when the robot uses the same genetic string to encode the synaptic learning rules, so the robot can learn during lifetime. And we want to see, first, will evolution come up with a behavior or with a strategy that is capable of solving this problem, so learning that the robot has to do something here to go to the light switch before it can go to the fitness to the light bulb. And second, is there a difference in whether evolution can manipulate the capability of learning during lifetime? We use a very fully connected neural networks. And first of all, if you simply look at the fitness or the performance of the evolved robots in the two conditions over generations, you see no difference. So these are generations on the x-axis, and on the y-axis is the fitness or performance of the evolved robot. When we evolve the weights and the robot does not learn, or where we evolve the learning rules but not the initial weights, you see that more or less the fitness is the same. So you would say, well, that's not a big difference. Well, yes, you see, if you evolve the learning rules, the robot reaches performance levels much earlier than in the case where you simply evolve the fixed weights. And 2, there is a small performance difference. But the big thing is how the robots solve the problem. If we take the best evolved robot in the case of when you evolve the weights but not the robot cannot learn, you see that what the robot does is that it does sort of stereotypical behaviors. It basically performs loops in the environment. It avoids the walls. We know that evolution can come up with collision-free navigation. And eventually, by using this minimalistic strategy, it will end up on the light switch. The light will go on, and then the robot displays a looping trajectory that is oriented towards the light bulb, and it will stay there. It's a very simple way and efficient to solve the problem, which many insects may use. Now, the situation is very different when the robot cannot encode in its own weights the geometry of the environment and cannot encode the reaction to the environment. It has to learn, if you like, on the spot how to solve the problem. And it learns it very differently. So what this robot does, when it starts with the random synapses, so at the beginning its behavior is still quite primitive, and then very quickly, as it is exposed to the light switch, it becomes attracted to the light switch, and then it starts, as it moves, it becomes attracted to the light, and then it will go very straight towards the light. Now, how can we test whether this behavior is really different from the one on the left? Well, we can change the environment and see how the two robots perform. And as I said, one way of changing the environment for these robots is to change the color of the walls. Now, if we change the color of the walls of the robot that has been evolved without a learning capability, this is the evolutionary environment that the robot has seen for many generations. Here the robot is capable of doing its minimalistic behavior and going towards the light bulb. We change the color of the walls. You see the robot hits the wall and is not capable of moving away from it. Again, here we change the color again. The robot is not capable of adapting to the new colors of the walls. So it hits the walls before, if you like, the sensory motor coordination is broken. It cannot anymore adapt to it. We take the robot that is capable of learning during lifetime, and you see that no matter what the color of the walls is, it will still display the same sort of strategy. We can also do a much more complex and tricky thing, is that we can change the layout of the environment. So this is the environment that the robot has been experiencing during evolution. The light switch is here, the light bulb is here. These are two fundamental landmarks for its performance. Now what we do is that we put the light switch here and the light bulb here. And that you see that the genetically determined individual is revealed. It does these minimalistic looping behaviors, and it will never end up on the light bulb. Instead, our adaptive individual, it will avoid the walls, locate the light switch, and then go towards the light bulb. We can even change the embodiment. So I should say, we are not evolving the individuals again. We take the evolved individual and we test it in different environments. We can disembody the evolved brains and transfer to a different robot. So we take the robot you've seen before with the 6 wheels and with a very different morphology, and we take the 2 evolved brains, the non-adaptive and the adaptive, we put it in this robot in a scaled-up version of the environment, and you see that the genetically determined robot will just keep moving with its looping mazes and will not be able to solve the problem, instead gain fitness. Instead, the evolved individual will adapt to this new morphology, will go towards the light switch, and then we go towards the light. Now, what this robot does is that you see that it moves backward, and then it periodically returns to the light switch. And this is why we said, why doesn't the robot simply stay here? Because the rubber wheels of this robot are a little bit outside the chassis. So as the robot approaches the wall with a small angle, it will climb up the wall, it will go back, and then it will keep moving forward, and it will try to go back to the light switch. That's the thing it didn't adapt to. So it's not perfect, but almost. So what you can see here is that evolution came up with something that is quite powerful. It solves a sequential problem where we do not provide intermediate rewards for solving parts of the problem, and it can solve it in a variety of different environments. So how many minutes do I have? 5 minutes. So I'll skip the predator-prey things. I want to talk to you about. I want to talk a little bit about the evolution of altruistic behavior and communication. Because we said consciousness is about sentience, is about living in an environment with other individuals. Now, a very strong form of social behavior is altruistic behavior. When you are ready to sacrifice, to pay a cost for the good of your community. Now, when we are talking of the problem in terms of evolution, in evolutionary terms, it means that the cost is that you have a lower probability of transmitting your genes for the next generations. And then the evolution of altruistic behavior is a problem for Darwinian theory, or at least the vanilla type of Darwinian theory, because Darwin said that, not Darwin said, but the vanilla interpretation of evolution is that individuals should always maximize the probability of transmitting their own genes to the next generation. Now, there are two hypotheses that biologists came up with that could explain the evolution of altruistic behavior, where an individual is ready to sacrifice its own reproduction for the community. One is the theory of genetic relatedness, and to make a story short, put forward by Bill Hamilton in 1964, the theory says that the more genetically related you are to your team members, the more likely you are to display altruistic behavior, because although you decrease your probability of transmitting your own genes to the next generations, you increase, by your altruistic behavior, you increase the fitness of your team member, who is very likely to carry the same genes as you have, and therefore you can indirectly transmit your genes to the next generation by favoring your kin. There is another theory instead, the theory of group selection, that says, look, it's not necessary to be genetically related to evolve altruistic behavior. All you need is to be able to work together with diverse individuals in a team, to be very complementary, and if as a team together you can perform a task much better than another competing team, then as a whole, all the team members will have higher probability of surviving, getting access to food, and transmitting their own genes to the next generation. Now, these two theories have had highs and lows over history, but there is no fossil record in evolution, and so it's not so clear how we can, and it's very difficult to do evolution of biological organisms because it takes a long time, especially if they are so sophisticated to live in colonies. And so what we decided to do is to test the two theories. We came up with two ways of designing the evolutionary approach so that we have either homogeneous, genetically related teams of robots, or genetically unrelated or heterogeneous teams of robots. And what we can decide is that we either select robots as a team, as in group selection you would do, or we select individuals independently of whether they belong to a team or the other. So, to make again a long story short, we can test whether either the theory of group selection or the theory of genetic relatedness, and we can see out of these four conditions, in which cases the robot display altruistic operation. The environment is very important, so to test this theory, we came up with this foraging arena, a set of small robots that have vision and have distance sensor of various types, are put in this arena, and they are presented with two types of food tokens. They are big food tokens and small food tokens. A small food token can be the robots can, imagine this is food. This food can be consumed only if the robots are capable of moving the food towards this wall. You don't see it in the video so well, but the wall is white. So the robots can distinguish this white wall against the black walls, the other three black walls. And if the robots can manage to put the food here, to take the food here, with an external camera, we can detect whether this has happened, and we can tell that the corresponding robot has gained fitness point or energy, which is good for reproduction. Now, a small food token can be taken to the nest, this white wall, only by a single robot. And the robot can feed on it. And it will consume the entire energy of the food token. Now, you also have big food tokens. The big food tokens contain enough energy for the entire colony. However, so if a big food token is taken towards the nest, every robot in the colony will get enough energy. It will gain, just like ants, they can take a big prey towards the nest, and everybody can feed on it. However, in order to push the big food token towards the nest, it takes at least 2 or 3 robots because they are very heavy. Now, there is a cost to pay, so you can either be selfish here and say, I take the small food token, I eat my own food, I don't care of the other. Or you can be selfish, and you can decide to go towards the big food token and hope that somebody else comes along and helps you. And the cost to pay here is that, as you will going to see in the video in a moment, to push a big food tokens towards the nest takes a lot of time. So the robots have a limited lifetime, so it takes a lot of time. 2, it's not guaranteed to succeed because of physical interferences. And 3, if the other robots do not help, you spend your entire life waiting for somebody else to help, and you will never get fitness point. So the question is, under what evolutionary conditions will robots display altruistic operation and go for foraging of big food tokens rather than small food tokens? And the answer is that, of course, if you have group selection or genetic relatedness, you will get devolution of altruistic operation. But the most powerful condition that we found is genetic relatedness. Group selection can work, but there are a lot of adverse factors that affect the outcome, which include noise in the environment, the coincidence of particular conditions for this to happen. Instead, whenever individuals are genetically related, you will always find devolution of altruistic operation. I want to show to you here the evolution of altruistic operation in the case of genetically related individuals. At the beginning, at generation 0, the robots do not even know how to move around. So here you see the nest, the white wall, and you see that the robots first, they don't even know how to coordinate their sensory perception with the motion. Sometimes they simply hit the wall, and sometimes they have catatonic behavior like this. They don't move at all. Now, if you wait long enough, you will see that after some time, the robots display a coherent behavior, and they will forage for the foods, for the food tokens. You will see that robots start to go for the big food tokens. They cannot move it. You get some few robots that are selfish, and every population can withstand a certain amount of selfish individuals. But most of the robots will go and help other robots to push the object. You see, this is a robot that encounters a small food token, but decides to avoid it to go and help these other robots that push the big food token. So you see, it's pushing a big obstacle like this, a big food token, is not easy. There is a lot of physical interference, and this is why there is a cost to pay. So if you are genetically related, you can evolve this sort of behaviors. And then we tested this sort of condition to see whether we could also explain the evolution of altruistic communication. So the evolution of communication is a big mystery, and we, in particular, and there is no fossil record for communication, and in particular, it's very difficult to explain why people would communicate or give away information that is very precious for their own survival to other individuals. And so we used robots that can communicate by means of light the position of objects that have the same appearance. So they are this red disk here, 1 and 2. In the photograph, this red disk looks like violet or purple, but as a matter of fact, it is red. So it's the same red as here. Now, this is poison. So if the robots go towards the poison, their fitness points will be decreased. Instead, if the robots go towards the food, their fitness points will be increased. And the robots have two choices. They can either communicate where the food or the poison is, or they can stay silent and decide to discover for themselves where the food and the poison is. And whenever you evolve these robots under condition of genetic relatedness, you see that the robots will start to use their colors to communicate, this is a food that is poison, where the food and the poison is. You see, this robot, this is the best evolved colony. This robot goes here, and then it turns blue. And the other robots have evolved a neuronal network that understands that blue means, hey, come here, here is the food. And you see that they will start moving here towards the blue. The more blue there is, of course, the more they are attracted. And as you're going to see now, the cost in doing this is that the more robots cluster around the food, the less space there is for other robots to go there. So if you communicate where the food is, then you will get a lot of robots there, and then eventually will not get enough food. So you see a robot going here. It cannot touch the disk, so it cannot get fitness point. It tries to go there, but it cannot. But eventually you will say, hey guys, here is food, come here anyway. And then you got that individual there looks lost, but eventually it will go towards the food. So So this is so powerful that you can actually evolve even very primitive forms of communication. And I have many other examples with flying robots, but I think I better stop here. And thank you very much for your attention.